Okay, I think this is this going? Oh, okay. Alright, seems to be going. Alright, no, not that. That's not what we want. This is what we want. Alright, sorry this took me a while. I just had to reconfigure my actual, like the physical computer, and I ended up getting the blue screen for a little bit. So oh, I need to reconnect my freaking remote control. Hold on. Remote control. Alright, we are good. Good to go. Alright, sounds good. Alright, I'm gonna blast through this because I have taken way too long. So yeah, I was reconfiguring my computer, and for some reason I got the blue screen of death for a little bit, so I just had to reconfigure some more stuff, and then I am now 12 minutes late. But alas, we are here, and we are back in the mathematics library. So yep, today we're going to be starting a new little, I don't know if I want to call it a unit, but just a new little section in this library, and we're going to be talking about graphs, graph theory. We'll be looking at representations, different algorithms, and then we'll be applying them to various situations, which will be pretty cool. So let's go ahead and start off with what exactly is a graph. So once again, I'm vastly unprepared right now. Let me just whip out my drawing tablet real quick. So when we are talking about a graph, we are specifically talking about just a connected, a system of connected nodes with edges or connections between the nodes that may be weighted or unweighted. So let's say we had a few nodes A, B, C, D, and E. And these nodes are completely arbitrary. What they represent does not matter at all. They could be cities, they could be network locations, they could be anything pretty much. They could be houses on a road. Those are all geographical examples, but in more examples you could see are in social networks. These could be, these could be people. So this was person A, person B, person C, D, and E, and so on. And they have connections between them. So A to B, B to D per se, C to D, D to E, and then also A to C, let's say. And these connections can represent anything, and it depends on the context. So if this was a map, these connections could represent roads. And now these can either be directed or undirected. A directed edge would mean that if this edge was directed from A to B, then an edge would exist from A to B, but not from B to A. And if this edge between B and D was undirected, then this means that you can go both ways along the edge. So B to D and also D to B. And then also another thing that we can do on edges is have weights. So for example, 5, 6, 13, 2.5, 7, 78. So these weights could represent how long it takes. So if it's a map, it could be the length of the road. In social networks, it could be the strength of the connection. So if A and B are, or if person D and person E are very connected, then it would have the edge would have a larger weight than some of the other edges. So yeah, you can, with just this little kind of vague framework that we have here, there's so many applications that you can represent just using nodes and these connections between nodes. And now the challenge becomes, how do we represent this? Well, for simplicity's sake, we're going to scratch the letters and we're going to use numbers for the nodes. So this will count 0, 1, 2, 3, and 4. And these will correspond to indices. And we can have these indices being in an array. So yeah, these indices would correspond to an array. And now the other challenge becomes, well, how do we represent the edges? So there are two major ways. So knowing that we have numbers for these nodes, let's look at the first edge representation, which is an adjacency matrix, which is an n by n array. So an n by n adjacency matrix is going to be where we have our rows. So these would be 0, 1, 2, 3, and 4. And then we would have 5 columns, 0, 1, 2, 3, and 4. Now the cell, so we'll say this is A. So A, I, J has a value, so it does not equal 0 if and only if an edge exists from I to J. So VI, VJ exists. And it's an edge, not a path. It has to be an edge between 0 and I and J. So for example, if we were to use an adjacency matrix here, we would have the cell 0, so this is going to be I, and this is going to be J. So we see that there's an edge from 0 to 1, so 0 to 1 will have a weight of 5. And if these edges were unweighted, then we could just put a value of 1 there, just so we indicated that there was an edge. So 5, now another one would be 0 to 2. 0 to 2 is 13, but this is an undirected edge, so it would go back and forth. So 2 over here to 0 is also 13. So it's a symmetric representation there. Then 2 to 3, I'll just make the rest of these directed. So 2 to 3 is 2.5, 2 to 3 is 2.5, 3 to 1 is 6, so 3 to 1 is 6, and then 3 to 4 is 78, so 3 all the way to 4 is 78. And to determine the neighbors of a vertex, and by neighbors I mean what other vertices you can directly go to, you just have to scan through the row. So for example, if we wanted to find all the neighbors of vertex 2, we would just have to scan through this row here. So we would scan, okay, column 0, there's a value. That means that there exists an edge from 2 to 0. And then these are all implicit zeros, so there's no edge there. And then we see 2 to 3 also has a value. Okay. Now the other way, now you can imagine, okay, this would become super complex and super inefficient if we had a bunch of vertices. So let's say we had 100 vertices. This array would grow to be 100 by 100, which is 10,000, I believe. Yeah, 10,000. And if we have an integer in each of these slots, that's going to be 400,000 or 40,000 bytes, which is a lot of memory. 40 megabytes just for an adjacency matrix. So the other way that you can use to you can represent this with is adjacency lists. And the principle here is that instead of having an array of arrays, we have an array of lists, which is kind of the same thing, but it's not a 2D array. It's just a list, or it's an array of lists. So we still have I being 0, 1, 2, 3, and 4, except this time, these slots will point to a list. And these lists will contain the neighbors of each vertex. So for example, 0 has neighbors 1 and 2. So in its adjacency list here, we would have vertex 1 with weight 5, along with vertex 2 with weight 13. Just like that. And for another example, let's do vertex 3, it points to 1 and 4. So 3 points to 1 with weight 6. And vertex 4 with weight 78. So now to determine the neighbors of a vertex, you just have to scan its adjacency list. So it becomes very, very simple in this way. And this is not n squared complexity. So this is the space complexity here is O of n squared. But the space complexity here is O of just n plus the magnitude of edges. So how many ever edges there are, that's going to be how many list nodes we have. So yeah, that's the second way, and we're gonna look at how to represent both those ways. All right, so let's hop into the code now. So we will start just by creating our graph structure, and we'll look at how to create a constructor for the graph so that we can have some flexibility. So I'm going to do this in our math library just because it's a big branch of mathematics. So we're going to create two new files here, graph.h and then graph.c. I need to organize these files a bit better. All right, so we'll start in the header file. We are first going to include, or let's not do our includes yet. So we're going to start with our graph structure. So we'll do a typedef struct, and then the structure will be an empty body for now, and we will typedef this to graph. Now in our graph, what do we want? Well, we want the number of vertices, so integer n, and the reason why we need this number here is because when we have an array, because the number of vertices is going to dictate the size of an array no matter what mode we use. So if we use an adjacency matrix, it's going to be n by n, but if it's adjacency lists, it's still going to be an array of lists, an array of n lists to be precise. So we're going to need that n no matter what. Now for the edge storage. So we're going to use a union here. So union, and then accompanying this union, we're going to have a character to represent the mode. So we'll call it adjacency mode. Now in this union, we're gonna have two possible values. We'll have an integer double pointer for an adjacency matrix. So this is how you represent a 2D array in C. It's just it's a pointer to a pointer. So a pointer to a pointer of the first pointer is to the first row, and the first row points to the first column of the first row, which is, or the first pointer there will point to the first integer in the array, so the first integer in the row. And then the other one we're going to have is a list pointer. So we will be using our dynamic array, which is included in the library up here. So include lib/dynamic_array.h, and then the second value in the union here will be dynamic array pointer adjacency lists, just like that. So we're going to have an array of lists here. Now for the mode, we're going to define two macros here. I'll have the first one is hashtag define adjacency matrix as 0, so false, and then define adjacency lists as not 0, so true. So if you remember our dynamic array, it stores a list of void pointers essentially, so an array of void pointers. Now we need to give it something to store. We can't just give it an integer because, well, when we need to store more than an integer, we need to store an actual. We need to store a weight with each edge. So we need to store an integer, 2 integers for the source vertex, the end vertex, and then the weight. So we're going to have a typedef struct here for the edge, and we'll call this edge. And in here we'll have an integer v1, integer v2, and then integer weight, where the integer v1 and v2 will correspond to the indices of each respective node here. Alright, then we'll have 2 constructors for the edges. So we both return edge pointers, and it's going to be create edge, and pass an integer v1 and integer v2, and then edge pointer return create weighted edge. Integer v1, integer v2, and then integer weight. And we can write these very quickly. Well, in graph.c we first have to include graph.h first. So for create edge, we're simply going to allocate memory, so edge pointer ret is equal to malloc size of edge, and then ret.v1 is equal to v1, ret.v2 is equal to v2, and ret.weight we're just going to say is 1. So once again, we're going to put this as 1 just because we want it to have some sort of weight. So if we go ahead and determine if this edge has weight, then the edge exists. If there is a possibility that we might have an edge with weight 0. This may arise in some algorithms where we still want the edge to be present, but we want it to have a 0 weight. So we're going to need to store the weight as 0, which would represent that it doesn't have any, you can't go along it. So that'll be a stored weight there, and then we're just going to return ret. Now for create weighted edge, it's the same thing, except we set the weight as the specified weight. So edge pointer ret is equal to malloc size of edge, ret.v1 is equal to v1, ret.v2 is equal to v2, and ret.weight is equal to weight. And then return ret. Alright, so that's simple enough. Alright, so let's go back into the header file now. Because now we're actually going to be looking at our graph methods. So these were our edges, the edge constructors. So I'll just put a comment here. And then we're going to have our graph constructors, or constructor. And this will just return a graph structure, and it's graph new. We just pass in a mode, and then an integer n for the number of vertices. Then we'll have graph modifiers. Oh, I also want to add a graph destructor here, so a void, return type void, and it's going to be graph free. And we pass in a graph pointer g. Right, as for the modifiers, we're gonna have the ability to add a vertex and also add the 4 types of edges. So void graph add vertex, graph pointer g, and then the 4 types of edges. So there's gonna be 4 different types, 4 different combinations of directed and undirected, along with weighted and unweighted. So the first one will be void add, or a graph add directed edge. Pass in a graph pointer g and an integer v1, integer v2. Then void graph add directed weighted edge. Graph pointer g, integer v1, integer v2, and then integer weight. And then void graph add undirected edge. Pass in a graph pointer g, integer v1, and integer v2. Once again, this will create an edge between both, so v1 to v2 and also v2 back to v1. And then void graph add undirected weighted edge. Graph pointer g, integer v1, integer v2, and integer weight. And then for the accessors, we will just have a void, or a character pointer return graph to string. Pass in a graph pointer g. So this will just return a string representing the edges and all the nodes. Alright, so let's start with the constructor and destructor. Okay, so we will have our graph return placeholder is equal to, we're going to use our initializer lists here. So the first parameter will be a null, because we don't know, this is just, or wait, sorry, let me make this, it's actually not null, it's going to be n then null. So we will pass an n for the number of vertices, then null, because this pointer, both of these are pointers, so we just want to pass a null since we don't know what it is yet. And then the mode for the mode here. Just like that. Oop, I need to include standard library to get the null keyword. All right, and now we're gonna set up our edge storing. So our edge storage. Edge storage. So first one is going to be if mode. So whenever we say if mode, that's going to revert to whatever this is. So that's why I define these as false and true. So if mode means if the mode is lists. So that's going to be throughout all of our methods. When we say if mode, we're saying if it's a list. And then else will be if it's a matrix. So if mode, we are going to set up our adjacency lists. So ret.adjacency lists is equal to malloc n times size of dynamic array. So what we're doing here is we are just setting up the array of lists. So allocate array of lists, and we allocate one list for every vertex. Now we want to initialize those lists. So for integer I is equal to 0, I is less than n, I plus plus. Then ret.adjacency lists at I is equal to dynamic array, default allocate, and pass in no parameters. So allocate each adjacency list. So we're simply calling the dynamic array constructor here, which will store that value in its array slot there. Now else, we want to allocate the adjacency matrix. So we're going to say ret.adjacency matrix is equal to malloc n times the size of an integer pointer. Because once again, it's a pointer to a pointer. We have an array of pointers where each pointer represents an row. Then for integer I is equal to 0, I is less than n, I plus plus. So this outer level for loop will always be the same, no matter where we do it. because we're going to be first iterating through each of the vertices, and that will be I goes from 0 to n. Whether we have each edge stored in a row or in a list, we're still going to have to iterate through each row and also each list. So we have to get there first. So at each row, we need to allocate the row. So ret.adjacency matrix at I is equal to malloc n times the size of an integer. So n by n. That's pretty standard. And the next thing we have to do is we have to set all the edges to 0. The reason why is because when we construct a graph, there are no edges initially. So we need to set all the weights to 0 and remove all those garbage values. So for integer j is equal to 0, j is less than n, j plus plus. And then ret.adjacency matrix at I at j is equal to 0. And then after all that, we're going to return ret. Just like so. Alright, so once again, for the matrix, we started with all of these values as being 0. So that means that there are no edges initially. And then for the lists, we start out with empty lists. So let's say that there was nothing there. This would be our initial state, but we would have allocated memory for the list. And the reason why we're doing it there, initializing lists now, is just to avoid any null checking when we want to add edges later on. Let me turn this down a tad. Okay, now for graph free, the destructor. Let me find it. It's copy. No, there we go. All right. So outer level check if g, and if g, then we have stuff to free. Otherwise, we have a null pointer. First, we have to check the mode. So once again, if g.adjacency mode, this is equivalent to saying if it's an adjacency list. Then we're going to go ahead and free each list. So for integer I is equal to 0, I is less than g.n, I++. Then we're going to call the dynamic array destructor. So dynamic array free deep, pass in a g.adjacency lists plus I. So we're doing a bit of pointer arithmetic here, where this just gets the ith pointer after this pointer here. So it just gets the next, or just, this is equivalent to saying a reference to g.adjacency lists at I. Except we're just skipping the reference, or the dereference, and then the reference to. And then we can free g.adjacency lists. And then else, we're going to have a for integer I is equal to 0, I is less than g.n, I++. Once again, same outer loop. And then we're just going to free g.adjacency matrix plus I. Same type of pointer arithmetic there, where we just get the ith row and free it. And then after that, we're going to free g.adjacency matrix. Just like so. I'm thinking about something here. Let me just see. Nope, that doesn't work. I want to test something out real quick, because I do want to do a reset method as well. So free, and then also just reset to clear, kind of. So void graph clear, passing a graph pointer G. So graph clear will, in essence, just remove all the edges but keep the vertices. Or do I want to do that? You know what, I'm not going to experiment with that right now. I will think about that later. But I'll just leave it like this for now. Alright, now we have our modifiers. So let's go ahead and do these these modifiers here. So we'll start with the edges, because these are going to be, this will be, I think, some of the most constructive, or the most, this will really show how the representation works. So we'll start with the add directed edge. So we first have to determine what type of edge storage we have. So once again, if g dot adjacency mode, then we're doing a list. So if this is true, we want to add an edge to the list. So we're going to say dynamic array add last. The list will be g dot adjacency lists plus v1. So once again, since we have indices v1, so let's say we wanted to add the edge 3, 1, we would go and seek the third list in the array. So this is adjacency lists, the pointer 2. Then we go three pointers down. So 1, 2. So down there, down there. Can I draw this actually? Yeah. So we start up here with the pointer, go down. I don't have my drawing tablet out. And then we also go down again to the third list here. And then we want to add it to the list. So g.adjacency lists plus v1, which is the index. Now the edge pointer that we're going to add is just using the edge constructor. So create edge. That's why we have the edge constructor as returning a pointer. So we can just pass it in here. And this will go from v1 to v2. Now otherwise, we need to set g.adjacency matrix from v1 to v2. So this is equivalent to at v1 at v2. And we're going to set this equal to not 0 or true. Once again, a non-zero value in this will give us or will indicate that there is an edge. All right, for add directed weighted edge, it's going to be similar, except we're just going to incorporate the weight. So I can actually just copy this if statement, because it's going to be the exact same, except the values that we set in the list and the matrix will be different. So for the matrix, we will just set the array value to weight. So now the cell value will store the weight of the edge. And for the list, it's going to be create a weighted edge, since we want to associate a weight, and we will just pass in weight as the parameter. So now for add undirected edge, it's going to be the same stuff. So I'm going to copy this if statement here, or I don't need to actually. So if g.adjacency mode, this is equivalent to saying if we have a list, we want to add 2 edges to 2 different lists. So dynamic array, add last. The first list will be g.adjacency lists plus v1, and the edge to add will be create edge from v1 to v2. And then the second edge to add will be dynamic array, add last, at g.adjacency lists plus v2 this time, since we're going from v2 to v1. So create edge v2 v1. And then otherwise, we're just going to set non-zero values in both cells. So g.adjacency matrix, add v1, add v2. So from v1 to v2 is equal to a non-zero value. Then g.adjacency matrix from v2 to v1 is equal to a non-zero value as well. And then for add undirected weighted edge, it's going to be very similar, except we're going to set the weights instead of a non-zero value. So each cell will be set the same weight. And then for the create edge, it's going to become create weighted edge. Just like that. And then we have to pass in the weight as the parameter. Alright, so those are the edge constructors, and then now we have to do the add a vertex. So for adding a vertex, it's going to be a little tricky here, because we simply can't, it's not as simple as just adding a list or adding a row. So there is a little more thought that has to go into this. So we're first going to store integer n, the new n, which will equal g.n plus 1. And then the last line in the method will be g.n is equal to n. Or we can make this add vertices. And we will pass in an integer n for the number of vertices to add, just to add a little more complexity here. And this n in the method will become next n, so integer next n is equal to g.n plus n, like so. And then we're going to have the same outer if statement. So if g.adjacency mode So if g.adjacency mode, we need to reallocate the list since we need to add new slots. So we're going to use the Realic method, which we have seen a few times before, but the process kind of goes like this. We first get a dynamic array pointer to the old memory, which is equal to g.adjacency list, so the original pointer. Then g.adjacency lists is equal to realloc g.adjacency lists n times the size of the dynamic array. So we want to reallocate the memory at g.adjacency lists to fit the size of n dynamic arrays here, dynamic array structures. Now, this may return null. So if not g.adjacency lists, we need to reallocate in a new method or in a new location. So g.adjacency lists is equal to malloc n times the size of dynamic array, or not n, next n, sorry. And this should also be next n as well. So we want to allocate for the new number of vertices. So next n, and there we go. That was unintentional. And then we want to copy over the existing memory. So memcopy g.adjacency lists. So that's the destination. Now the source will be the old memory. So old memory, and then the memory to copy will be g.n times the size of the dynamic array. So we're copying over the original n, or the original dynamic lists here. And now we need to set up the new lists. So allocate new lists. So for integer I is equal to 0, I is less than n, I plus plus. then we're going to say g dot adjacency lists at I plus g dot n. So we're starting at g dot n and counting up from there to account for the new vertices. And this is equal to dynamic array default allocate. And then at the end, we can, or before this loop, I guess, we can go ahead and free old memory. Since the memory has been copied over, we don't need this pointer anymore to the old memory since it's in a new location, so we can just free that pointer there. Alright, now else. This one's going to be a little, it's going to be somewhat similar, but there's going to be a little, some more stuff that we have to do here. So we're going to start in a similar fashion, but not really. Oops, this should be else out in the outermost block. So for adjacency matrices, we don't have, thinking. You know, I think the way I have it is simplest, yeah. Okay. So we're going to have an integer pointer, new adjacency matrix. And this is going to be malloc next n times the size of an integer pointer. Then for integer I is equal to 0, I is less than n, I plus plus. So we're going to iterate through each row. Now, in each row of the new adjacency matrix, we need to allocate some memory. So new adjacency matrix at I is equal to malloc n times the size of an integer. Now, if I is less than next n, or if I is less than g dot n, then we want to copy the memory over because they're existing values. So for example, in this adjacency matrix here, if we added an additional row, like if we added a 5 here, and maybe a 6, then we would want to copy the first 5 rows. So if I is less than g dot n, which is still 5, then we want to allocate or copy over the memory. So if I is less than g dot n, then we're going to say we're going to set memcopy, or we're going to do memcopy. The destination will be new adjacency matrix at I. The source will be g.adjacency matrix at I. And the number or the size of the memory to copy will be g.n times the size of an integer. And then we need to set the rest of the values to 0. Or the rest of the values in the row to 0. Because remember, when we add vertices, we're going to be allocating new columns as well. So we have, there it is. So we have 5 and 6 as in our new columns as well. So for integer j is equal to 0, j is less than n j plus plus, then g dot adjacency matrix at I at j plus g dot n, same sort of accounting there, is equal to 0. So just set the values to 0. Now otherwise, we're going to allocate, or we're going to set all the values to 0. Now I'm going to test this out. I'm going to test out memset. I'm not sure how memset works, but you know what, I will figure that out later. But for now, we're just going to make it simpler and we'll use a loop. So for integer j is equal to 0, j is less than next n now, and j plus plus. So since we have an entire row to fill, we need to go from 0 to next n and set all the values to 0. So g.adjacency matrix at I at j is equal to 0. So set the entire row to 0. Alright, and then just like that. And then once we're done here, we can free up some memory. So at the end of each iteration, we can go ahead and say free g.adjacency matrix at I. And then after the entire loop, we can say free g.adjacency matrix, and then update the pointer. So g.adjacency matrix is equal to new adjacency matrix, just like that. And then the last line is g.n is equal to next n. Alright, so once again, just to recap on what these variables are. N, or g.n, is the initial number of vertices. N is the additional number of vertices to add. And next n will be the total number of vertices at the end. So when we're allocating new lists, we want to allocate next n, since we want to allocate memory for the new, for the total number of vertices. And when we want to iterate through, and when we want to copy existing memory, we're going to, or when we want to copy existing memory, we're going to use g.n because that's the only memory that exists. When we want to set the new memory, we want to iterate from 0 to n, since that is the additional number of slots or arrays that we're adding. And so that exists here, also, or this loop here, when we, the outer loop in the adjacency matrix should be I is less than next n, since we want to allocate or iterate through every single row here, the total number of rows. Oh, sorry, and then this free old memory for the adjacency matrix at I, so the old memory, that should be within this if statement here. So if I is less than g.n, then we want to free it, because otherwise we'll be freeing non-existent rows and that will give us errors. So we just want to free that old memory within this if statement here. Alright, good shit. Alright, and the last thing we want to do is graph toString. Or not the last thing, but this is going to be the last method in this section, and then we're going to take a bit of a break. Or we will test and then we'll take a bit of a break. Alright, so for toString, we first have to include string stream, which is included in the library here. So include lib/strstream.h. Alright, and then we're going to have our string stream ret is equal to string stream allocate g.n. And then at the end, we're going to return ret.string. Alright, so our outer structure will be a for loop for integer I is equal to 0, I is less than g.n, I++. So we're going to add a new line, or a new, we're just going to iterate through each vertex. And then we will have our if statement to determine the mode. So if g.adjacency mode, if we have our lists, we need to iterate through the list. So we're going to say edge pointer e is equal to null, and we're going to use our dynamic array iterators. So dynamic array iterator, it is equal to dynamic array iterator new, and the list to iterate through will be g.adjacency lists plus I, and then while e is equal to dynamic array iterator next, passing a reference to it, has some value, so while we get a value from dynamic array iterator, or the next method, we're going to say if e.weight, and we want to print out the string. So string stream, concatenate, pass in a reference to ret because we want to concatenate to return. The format will be %d to %d. You can format this however you want. I'm just doing it like this. So %d to %d, and then %d for the weight, and then back to the new line. And the three values will be e.v1, e.v2, and then e.weight. So that's that. Now else, if it is a matrix, so if it's an adjacency matrix, we need to scan through the row and then print or output edges. So for integer j is equal to 0, j is less than g.n, j plus plus. Once again, since this is an n by n matrix, we have g.n rows and g.n columns. And then we're going to say if g.adjacency matrix at I at j is equal, just if this has some value, then we want to output the same thing. So string stream, concatenate, pass in reference to ret, %d to %d with weight, %d, new line, and this will be from I to j with weight, g.adjacency matrix at I at j, which holds the weight. So you can see the similarities between the two methods here. We still have the same outer loop for all of them. It doesn't matter because it's the same for each vertex. Now, within adjacency mode, we check if each edge has a weight, and most likely they will. The only time they wouldn't is once again when we have an algorithm that may decrease the weight. But for the printing, this will mainly just result a true. But this if statement here is equivalent to this if statement here. So this and this, I can't highlight them both at the same time, but this and this are the same if statement, if a weight exists on the edge. It's just the loop that is different, and it's the number of times we'll have to loop to get that. And then at the end, we just return ret.string. Alright, so let's go into the test folder. We need to add our graph.c to the build path here. And then in main.c, let's delete everything we have. And let's set up some things here. So we'll have a graph g is equal to graph new, or we need to include, sorry. So include C mathematics / graph.h. So graph new takes in two parameters. The first one is the mode. We'll do adjacency lists first, and then n, which will be n, and we will store n as a variable. Integer n is equal to 6 for now. Or we can actually just do this here quick. So this would mean that n is equal to 5. Oops. Alright, so let's add our edges now. So graph add, we'll start 0 to 1. So graph add directed weighted edge. This goes the to graph in graph G from vertex 0 to vertex 1 with weight 5. Then we'll do 0 to 2 graph add undirected weighted edge. This is in graph G from vertex 0 to vertex 2, and the weight is 13. Then let's do vertex 2 to vertex 3, so graph add directed edge. Let's just act like this weight doesn't exist, so we can just see how this works here. So draw. Just let me delete that. So there's no weight there. So we just want to see what that is. So in graph G from vertex 2 to vertex 3. Then we'll do 3 to 1 and then 3 to 4. So graph add directed weighted edge in graph G from vertex 3 to vertex 1 with weight 6, and then graph add directed edge in graph G from vertex 3 to vertex 4 with weight 78. Alright, then let's get the value here. So character pointer string is equal to graph to string, passing a reference to G, then printf will print out the string, and then free the string. And then we'll call graph free at the end with a reference to G. Alright, let's run this. Oops. We have an error somewhere. Oh, this is directed weighted edge first. And then in main.c we also have to include standard lib. Alright, that's fine. Alright, let's check out what we got. So we have 0 to 1 with weight 5, then 0 to 2 with weight 13, 2 to 0 with weight 13 since it's an undirected, so both edges exist, then 2 to 3 with weight 1, that just means that there is a weight, so the edge exists, and then 3 to 1 with 6, and 3 to 4 with 78. Now let's try adding a new vertex. So graph add vertices, passing a reference to G, and we will add, let's say two new vertices. Or first, let's just check this with the matrix just to make sure this works as well. So adjacency matrix, just like that, and then run it again, and we get the same thing, so we're all good there. Alright, so let's try adding a vertices too, and then we will add, let's do graph add directed weighted edge in graph G from vertex 0 to vertex. We now have 7 vertices, so vertex 0 to vertex 5 with weight 16, and then graph add undirected weighted edge in graph G, or just undirected edge in graph G from vertex 3 to vertex 6, no weight, and then we will do the same thing. Just print out or get the string value of the graph. And then we'll print that out. Uh-oh. Let me see, alright. Where did it... Oh no, where did it... Okay. Where did it do this? Alright, so it's definitely an add. Alright, let me just make sure that add, okay. So it's in add vertices. Alright, so we'll debug. Breaking graph.c at line 89, and then we'll just run here. Alright, so print next n should be 7, good. So we're going into this if statement here. Oh, this should, oh, okay, I know why. Yep, okay. So when we allocate each row in the new adjacency matrix, this should be also be next n and not just n. I mean, that's, I guess, self-explanatory, but I just forgot to change it. So now when we run this, we should get, we still don't, damn it. Alright, so new adjacency matrix. Good. Good. If I is less than g dot n, so if the memory already exists, we want to copy the memory over. And then go from, oh, wait. Wait, no, that looks right. Set 2 new values, good. Oh. Why does it not like that I'm freeing the old memory? Alright, let me try freeing all this memory after the loop, or after, yeah. Alright, let's run this now. Nope, still doesn't like it. Alright, oh, no. Oh, god damn it. Okay. I know why. Alright, so this is okay right here. This free statement is here. That's good. Except when we're setting the new values, we're setting them in the old matrix, which doesn't have enough space. So we need to set this in new adjacency matrix. Okay, that makes sense. So there and then there. Okay, that is completely my mistake. Yeah. And there we go. We have the new edges. 3 to 6, 6 to 3, and then also 0 to 5 with weight 16. That's good. So yeah, make sure that when you're setting the new edges that you're setting it in the new matrix, just because it'll screw you over with memory. So yeah. Okay, so that's the basic part of just the graph introduction. So just representation. Now we're going to look at a very simple traversal method. So let me grab my drawing tablet again. And I'm actually just going to remove our addition, or our vertex addition here. Alright, and I'm going to copy this graph over. Alright, so let's look at this graph here. So now that we know how to represent this in code, we need to look at what we can do with it. So a good place to start with would be searching. So let's say we have our initial node 0. So this is our start node, and we want to find 4. So how would we get to 4? Well, it's easy to look at this here, where we go 0 to 2. I can't draw. 0 to 2, 2 to 3, and then 3 to 4. Now why can't we go 0, 1, 3, 4? Well, we can go 0 to 1, but we can't go 1 to 3 because an edge only exists from 3 to 1, not 1 to 3. So this does not work here. We could go this way, however. So But how do we deduce this? How are we gonna systematically devise a process to say, okay, 0, 2, 3, 4? Well, we're gonna go back to our representations, and no matter how we represent it with a list or a matrix, we know all the neighbors of 0 immediately. We just have to either scan through a list or a row. So what we're gonna do is we're gonna create a kind of, so the method would be, okay, we see that 0 points to 1. Now what does 1 point to? 1 points to nothing. So we stop there. 0 also points to 2. 2 points to 3. And then 3 points to 1. 1 points to nothing, so we stop. 3 also points to 4, which is our goal. So then now we have a path here. We go 0, 2, 3, and then 4, which is our goal. So our path P is equal to 0, 2, 3, and 4. So we kind of have a systematic structure here. And you may recognize this, or you may be starting to think, okay, well, method-wise, this is starting to look like a stack, right? Because we have 0, then we go through its neighbors. Add its neighbors to the stack, let's say. 2 to 3, 3 to 1, so on and so forth. We could do this with a stack. We're going to do it using recursion today. Just think about it. The structure of each subproblem is exactly the same. We are just iterating through each vertex's neighbors. So the neighbors of each vertex, we just want to go through whether it be the list or the row, but it's still going to be the same structure. We're going to have a for loop or a while loop that just goes through each of the neighbors, and we're going to recurse even further down. Now, efficiency-wise, a stack would definitely be the safer option, in my opinion, because with recursion you can get quickly into overflow, or stack overflow, where the call stack just grows too large. But for now, we're just going to do the recursive method. So let's start in graph.h in the header file, and we're going to create 4 new methods. So we're going to start with a void graph start, or graph DFS start. We will take in a graph pointer G, and then we're also going to have 3 other arrays here. So we're going to have an integer pointer D, an integer pointer F, and an integer pointer P. So D will represent the discovery times. So for example, if we start at vertex 0, this will have a discovery time of 1. So this is 1 slash, and it'll be the finish time. So 1 slash whatever. Now we go to 1 first. This has a discovery time of 2 slash whatever. And then we see that there are no neighbors, so it also finishes at, or it finishes at 3. Then we go to 2, discovery time of 4. No finish time yet. Go further into 3, discovery time of 5. Nothing yet. No finish time yet. And then go to 4, which is our goal. Discovery time is 6, finishes at 7. Then go back. 3 finishes at 8. Then 2 finishes at 9. And finally 0 finishes at 10. So we increment the time for every step that we make. So this will be kind of our discovery and finish time. Now what this will help us do is it will help us avoid an infinite loop. Now we could look at using a visited array to avoid cycles. So for example, if we had vertex A, B, and C all connected like this, and we did a DFS, we would start at vertex A, then go to C, then go to B, but B goes back to A. So if we had no check to see if A had been discovered yet, then we would just keep going in this circle and, yeah. Alright, sorry about that. I just had to talk to something real quick. Alright, looking good. Yeah, we're going. Yes, we're going through. Alright, so yeah, to avoid a cycle, we are going to keep track of the vertices which we have discovered, but it may also be helpful to figure out which vertices we have finished first. So we're going to start with DFS start, which we will pass in just pointers to erased output to. And this P array here, will give us the parent array. So each vertex will have a parent that we discovered it with. So we can start with here, so the parent of 0. So the parent of 0, or sometimes called predecessor or pi of 0 is equal to 0. Then we have a pi of 1 is equal to 0 because we discovered it with that. Then pi of 2 is equal to 0 as well. Pi of 3 is equal to 2. Now, at 3 we look at 1, but we see that 1 has been discovered already because it has a discovery time that is not -1 or not 0. So when we say, or when we see this here, we're not going to update the parent, we're just going to skip it. And then pi at 4 is equal to 3. So this will give us kind of a predecessor tree, and what this will allow us to construct is a forest. Or for now, I'll talk about a forest later, but for now we will just look at this as a predecessor tree. So this will give us kind of the first, or this isn't a least or a lowest weight tree, but it's just a tree that allows us to, a spanning tree. So we see that it goes, so looking at this predecessors, we would see that it's just the red. So the red is our spanning tree, except we don't do that and we don't do that. So our spanning tree is 0 to 1, 0 to 2, 2 to 3, 3 to 4. And from this spanning tree we can get to each vertex. So that will be the P array there. Alright, and then we will have our method, which will actually be the recursive method, so void graph DFS, and this will take in a graph pointer G, an integer source, or I forgot we also have to pass an integer source here for the starting of the DFS. So the source there, then an integer pointer D, integer pointer F, integer pointer P, and then also an integer pointer time. So as I said before, we're going to have times to represent which vertices have been visited, but that will need to be passed across the recursive level, so we'll have a pointer here. Alright, so let's copy and paste these definitions or signatures over into graph.c. And we will start with DFS start. So for DFS start, we're going to initialize a time variable, so time is equal to 0. Then we're going to initialize all of our array values. So for integer I is equal to 0, I is less than g.n, I++. Then we're going to set d at I is equal to 0, f at I is equal to 0. So this is assuming that these arrays have pointers or have some output value that has memory allocated. And then p at I is equal to -1 to indicate that there is no parent yet. And then we're just going to start from the source. So graph DFS. We're in graph D. The source will be the source that we passed in. The D array will be D, F is F, and P is P, and then time will just be a reference to time. Now for DFS, the first line will be if not visited source. Or wait, not. Or not, sorry, this is the wrong method. So in graph DFS, we're first going to say, we're going to increment the time. So time, so dereference time, make sure you put parentheses around these, and then do a ++. So we get the dereferenced pointer and then just increment it by 1. And then d at source is equal to time, since we discovered this vertex at time. Or this should be a dereference of time. And then we want to discover the neighbors. So if g.adjacency mode, so once again we're doing our if statement here. So if we have lists, so if g.adjacency mode, then edge pointer e is equal to null. This is just going to be the iteration. So dynamic array iterator, it is equal to dynamic array iterator new, pass in g.adjacency lists plus source. And then while e is equal to dynamic array iterator next, pass in reference to it. And then we want to determine if this edge has weight. So if e.weight and not discovered e at v2. So this if statement is if the edge has weight, so is valid, and the vertex has not been discovered. So if the second vertex in the edge does not have a discovery time, it has not been discovered. So what we're going to say is we're going to recurse down. So graph DFS g e.v2 and pass in the same arrays. So v2 is now the source. So as with here, we go 0 to 1, and then we start DFS again from 1, so on and so forth. So e.v2, second vertex and edge, the same arrays, d, f, and p, and time will be the pointer. And then we set the parent. So p at e.v2 is equal to source. All right, now otherwise, we're gonna scan the row now. So here we want to iterate through the edges, and if we're in an adjacency matrix, we want to scan through rows. So for integer I is equal to 0, I is less than g.n, I++. And if g.adjacency matrix at source at I and not d at I, so the same sort of check. So edge has weight, valid, and second vertex not yet discovered. So then we're going to recurse down. So graph DFS in graph G start at vertex J this time, or vertex I, sorry. And then D will be D, F, P are the same, and time is also the same pointer there. And then we set the parent. So P at I is equal to source. And then at the end, we want to set time plus plus, since we want to increment the time and then set the finishing time of the source. So f at source is equal to time, just like so. All right, let's go into main.c, and I just want to print out the parent or the parent array here, or all three arrays rather. So I'll just have a method here, void print integer array. So I'm in main.c and I'm just going to pass in an array r and integer n for the number of things. So print f and for int I is equal to 0, I is less than n, I plus plus, then print out we'll print out the array at I, and then just print out a new line. Okay, so now let's do a DFS through our graph here. So we will start by creating our arrays. So it's going to be, we need df and p. So integer d has size 5, or we'll just say integer pointer d is equal to malloc n times the size of an integer, and the same for f and p. Alright, then we're going to call graph DFS, passing in graph a reference to G. We'll start at source 0, and then D goes from, or just, we pass in the arrays D, F, and P, or this should be DFS start rather, since we don't have a time yet. And then we can print out the three arrays. So print integer array, D, N, and then we can free df and n as well. Or df and p, rather. Alright, let's run this. Alright, finishing times did not work, but the starting times, or I think I know why. Oh yeah, so this should be a reference, or a dereference of time when we set f at source. So let's run this now. Alright, so let's compare this to what we had here. Alright, so starting time for vertex 0 is 1, and finishing time is 10, parent is -1. I just wrote 0 here, it doesn't matter, it's -1. For vertex 1, we have 2, 3, 0. Then vertex 2, we have 4, 9, 0, correct? Vertex 3, we have 5, 8, 2, and then vertex 4, 6, 7, and 3. Good fucking shit. Alright. So yeah, that is pretty much the basics of graph theory, or I wouldn't say that all the basics of graph theory, but we did a good amount of stuff today, with representation wise, which is all cool. So we have our DFS, and I will add some flexibility there on what you can and can't, or on, you could probably have multiple sources if you wanted to, but for now we will just leave it like this. And the next time I think we'll be working on some algorithms, or on stack version of DFS, which will be a little different, and stuff like that. So yeah, I hope you guys enjoyed this. I do want to go back to OpenGL, but I need to figure out where to start with that. But that'll be next time. But yeah, anyways, hope you guys enjoyed this. Hope you learned something, maybe. I hope you do, or hope you did. It'd be cool if you did. But yeah, next stream should be a lot smoother in terms of me getting there on time, just because I'm all set up now and I know what to expect in terms of what I need to do. But yeah, so I will see you guys next time. Keep yourself safe and have a good one.